All right. Welcome everybody. Uh, how's everyone doing? How are your labs going? Good. Good. Bad. Okay. Awesome. Um, yeah, I try to tailor this to match with your labs. So, for some people who've already had the second lab, it's going to be a lot of kind of the same things in today's class. There's going to be like an example heavy class. I'm going to do like example after example today. I don't have too many like physical demonstrations for the class today. So if you want to follow along, I'd suggest everyone just like go through your own calculator, see if you can get it before I can. All right. Starting out, we left off with some free body diagrams. These are just sort of diagrams that summarize the forces acting on an object. So from last time, we want to sum up the forces. We could do that just by drawing a diagram. It'll help us a whole lot. So in my examples from last time, I'm going to just go through this. So we had just like a book sitting on a table somewhere. And we just finished learning sort of the basic three laws, Newtonian motion. And this was springing off of Newton's third law, which was every action has an equal and opposite reaction. And I gave you guys a question of why isn't this book moving? Sort of staying still on this table. Staying still because the table is holding it up. So we've already seen before from like motion of projectiles or things moving in the air that everything on Earth has a downward acceleration all the time, everywhere. Even you, while you're sitting there, not really doing much. Same as this book, it's accelerating downward. It's just the table is stopping it. So there's an acceleration downward. This book has mass, and so we have a force downward. Need those. So we have, I can draw a picture every time. Maybe I don't want to, but I think last time I had something like this, where it was just the book, and you're just labeling the forces with arrows. Where are they directed? So the force of gravity, F sub g, is downward, and the normal force, that is the contact force between a surface. The normal force is what's holding the book up. So I put F sub n. Then your book just has it as n. I don't really like that, because I want to always remember that that is a force. It's pointing upwards. It's pointing up just in this case. Next example, the book is moving with a constant velocity. So say it's on the table, but I am sliding it at a continuous rate. So it's not speeding up or slowing down, it's at a constant velocity. Be a very similar picture. And why am I doing this dot in the middle? That's just to show you that if you didn't want to draw a book every time, you could just make the whole thing a dot, just like this. Same as this picture over here. So we have the table, even though I'm sliding this book, the table's still holding it up. So it's still pointing upward even while it's moving. The book still wants to accelerate downward. So there's still that downward gravitational force. But the book is not accelerating in any direction. It is moving at a constant velocity. And remember that acceleration was the change in velocity, so we will look back or like reflect on Newton's second law, which said this. Newton's second law, F equals ma. So constant velocity is not accelerating. Acceleration is 0. So there's no force in that direction. Now it's kind of hard to see. I have my hand on this. You gotta imagine I'm on like an air hockey table, and I give it a little push, and it goes. So that's the case there. Finally, the book is accelerating to the right. We have the table holding it up as the normal force. We have the force of gravity trying to pull it down. But now I am accelerating it in the positive x direction. So I have a force to the right. I think last time I didn't label this. I should have. So F, I'm just going to say push, because I'm pushing it. Force sub push. So I can label these whatever I want, just so I know what it is. I'm pushing it that way with the force. Okay. That's where we left off. So we're I wanted to review these because we're going to use these, heavily in my examples today. These are going to help us imagine the picture in our mind so we can add the forces easier. All right. First, before we get to the examples, we need to talk about weight. A lot of the time, here in the U.S., we will step on a bathroom scale or, order something online, and it's given in pounds as the weight. Now, you got to remember, weight is not the same thing as mass. Let me put that up here. Weight does not equal mass. When we are finding weight, we are finding a force. So the unit of pounds is how much you are forcing into the ground. I could also find your weight, or you could actually buy a bathroom scale that measures in newtons. How many newtons do you weigh? That's a force. And on Earth, so like that, same sort of example with the box. I've been seeing F sub g as the force of gravity downward. That's the same thing as the weight of this object. And sometimes people call that just W for weight. But it is important to remember, weight does not mean mass. Mass is how much stuff is in the object. Weight is how much does it force into the ground. Okay, let's see. Yeah, so in this case, I have force of gravity is down, and that equals the weight. So let's rewrite this equation. Force of gravity is, I will rewrite Newton's second law. So instead of mass times acceleration is mass times gravity. And since weight and the force of gravity downward, that is the same thing. We'd also say that mass times gravity. All right. I think the final thing before I leave this slide, I can't come back to the slide once I pass it. I need to make sure I go over, I don't know if I have already, what the units that we need for a force or anything. So let me, let's go like this. I made that too long. Right. So Newton's second law, force is mass times acceleration. At the time I was like, I'm missing something. This is what I was missing from that slide. I wanted to put in the units. So the unit of force, that is 1 Newton. The unit of mass, that's a SI unit of kilograms. And the SI unit, or units we're looking for this acceleration, is meters per second squared. Okay, I just want to, I think I forgot to officially put this somewhere. 1 meter per second squared. There we go. Okay. So we should have everything for this next example. Is starting out easy. 10-gram box sits at rest on a table. What is the magnitude of the normal force acting on this box? Okay, let's first start with a picture, or at least a free body diagram. So, what do we have? Going to do just the free body diagram, no picture. So we have this sort of dot, that's the box. So it has a force of gravity downward. And it sits at rest, so it's not moving. We have the force, normal force, pointing upwards. Just like that book right there. We just want to find the size of that normal force. We want that value right there. Since it's not moving up or down, that means that the force downward is the same as the force upward. So let's find the force of gravity, or the weights of that book. All right. So we have the weight equals mass times gravity. I think everyone should know already by now that gravity is 9.8 meters per second squared. What's the mass that we need to use? We need to use kilograms, right? We need to convert that value. 0.010 kilograms times. There we go. Someone with the calculator, if you could help me out. I don't have anything up here. So we will find this weight of this book, forcing downward. That should be 0.09. Yeah, so 0.09, right?
Do you know what the negatives are?
0.98. 0.98. So that is. Sorry?
There's a 0 before the 9.
Okay. There we go. Newtons. So this is weight, it's downward. We can have negative value, that's fine. In fact, yeah, let's do that. So let's say, well, actually, I'm going to do this instead. Since we know it's not moving up or down. Oh, no. I remember. Going too fast. So we found the force that it's exerting downward. So now let's sum the forces. That's the big thing for this example. So let's sum the vertical forces. Sum the vertical forces. I'm going to write right here, sum forces. Okay, so there's only two in this problem, one going up, one going down. So we have normal force plus the other force that is moving vertically, and that is the weight, and that's where we put the negative sign on the value. So I am putting the negative there. And that equals how this thing is moving vertically. So in this case, it's very easy. It's not accelerating or moving up or down. So that's what this A sub y means. All right. So we have the normal force minus 0.098 equals 0. That's because it's not moving up or down. And that's why we can say, certainly, what the value is. And it is positive because it's going upward. Okay. So this one was easy. I could have just sort of, found one and said it was the other right away. I was starting to do that, but then I realized I needed to go a bit more detail so it can help us for this next problem. All right. Next up, a 55 kilogram shopping cart. It's initially at rest on a horizontal surface. The child begins to push the cart with a constant force. And it's going in the positive x direction. So let's make, I don't know, I am going to draw this time. So it's going, that way. I don't want to draw a shopping cart all the time. So I'm going to make this just a free body diagram with just a dot showing where the forces are. Yeah. Okay. So shopping cart's on the ground. So it's not moving through the ground or it's not going up into the air. So that means that force of gravity downward, or the object's weight is downward, and it's equal to the normal force that's holding it up. So it's, staying on the surface. However, it is accelerating to one direction. And I'll say this is the same thing. I'm going to say F push, because it's being pushed one direction, positive x direction. Okay, so now the big sort of thing we always start with is summing the forces. So I didn't even bring the question up. So I've drawn over it. What's the total acceleration of the shopping cart? Okay. Let me redo that. Okay. So going in one direction, we're going to sum the forces, and we're going to keep the components separate. So we're going to sum the vertical forces, and we're going to sum the horizontal forces separately. So let's sum the vertical ones. I have a feeling I have one more part to this question. Hold on. No, okay. So in this case, since it's not necessary, I'm not going to do the vertical. I changed my mind. What's the total acceleration? We are seeing that it's going to be moving to the right. So let's sum the horizontal acceleration. So there's nothing forcing it to the left. It doesn't say that there's friction or any other kinds of forces. There's only one force going to the right, and that's the force of the push. And it's moving at a specific rate, a specific acceleration. That is 2. No, it doesn't give us the acceleration. We want to find the acceleration, right? Horizontal acceleration. And this is where we can say that, I can just take these values. F push equals max. All right, what are these values? Let's put them in. 55 kilograms for the mass of the shopping cart. We have 2 newtons for the push. And we have an unknown acceleration over here. And since we have these in the standard units, newtons and kilograms, we don't have to look up what the acceleration will be. We'll just know, just by doing the division right here, that the acceleration will be in meters per second squared. So what do we have? Acceleration is What was that? 0.6?
0.036.
0.036 meters per second squared. Okay. Awesome. So the first one we summed vertical forces. This one we are summing horizontal. This next one, I think it's this next one, might be, yeah, maybe a little both. Okay. Go like that, both them up before I draw a picture. Okay. Person is pulling a sled on some snow, and they're not pulling it directly horizontally. They're sort of pulling it, you know, like on a string or like on a rope. And they're up here, the sled is on the ground, so that makes it kind of angle between their hand and where the sled is. If I can maybe make a picture, I'll show it like this. So like that. So they're pulling at a specific angle. It's not completely flat. They got some height to it as well. They're pulling at that kind of angle upwards. You see, this picture can become very messy very quick. 25 degrees above horizontal. And we want to find some things about this. So let's simplify this whole situation with the free body diagram. Put it right here this time. Okay, so pulling this thing, I'm assuming it's not like, you know, jumping in the air or like being forced into the ground by me pulling it. It's just going to be sliding on the ground with me. So I know everything has a force downward. Or a weight, since it's not, you know, rising or lowering. The normal force is the equivalent, but in the opposite way. And it has this new force that's at a weird angle, 25 degrees above horizontal. So let me make that. Let's say I'm going to call this pull. Force of the pull. Okay. We also know the mass of the sled. The mass is 80 kilograms. That will help us. It's already in an SI unit. What else? What else do we need? All right. First one, find the horizontal acceleration. So we need to sum the horizontal forces. Okay. But what are they? There's nothing going to the left. And this one, like, it's going at an angle. It's not all going to the left. So what do we need to find? We need to break that one vector up into its components. So we need to find the x component of that sort of slanted vector right there. So we need to find, make this like bright red. Pull x. So that's the horizontal component of that slanted vector. And eventually, you're going to see it from that other part, we're going to need that vertical component as well. So this blue vector right here that is y. This is pulley. Let me just make this like f sub p, so I don't have to spell, you don't think this is like a word. Px and py. So you say force from the person. That's fine. Okay. So now we've broken this vector up into its components. Now we know there is one vector going to the right that is completely horizontal. Awesome. That's the red one. And that is equal to, the mass of the object and however fast it's moving over there. However fast it's moving horizontally. I should be more specific. So it's always going to equal ma(x) for the horizontal. It's always going to equal ma(y) for the vertical. And then we judge to see how it's going to move. In this case, we want to find that value. So, what do we need to do? We need to find the actual value of fpx. So, I'm not going to go through every step. P, that's going to be cosine of 25 degrees. And that equals 150 times cosine 25 equals, I'm just going to put the mass in as well. You see, I have everything now except for that horizontal velocity, so I can solve for that. I don't have a calculator up here, so let me know when you find it. 1.699. All right. I'm going to run out of room, so I'm going to put it right here. Nope. Meters per second squared. Awesome. Done. Next, we want to find the normal force of the ground acting on the sled. This could be important if we're like, we need to, figure out how much force a bridge can take. Okay. We need to sum the vertical forces. Okay, now what is acting vertically? I've already broken it up into pieces. So we have two things pointing upward, one thing pointing downward. We're still going to sum all of them together. So I'm going to write it like this first. And then I'm going to add the negative values when I see it's appropriate. See, one of them is going to be negative because it's pointing downward. Okay. So we're solving for normal force. Let me just put everything in without doing too many steps. Okay, So that vertical component, that is going to be FP sine of 25. And so I'm going to write it like this. Actually, yeah, let me write it. FP sine of the angle All right, we have keep losing it, 150. The mass of the sled, that is 80 kilograms. This is gravity, 0.81. And we're going to see that these things could cancel. I'm just writing it all out in full. Well, actually, sorry, hold on. It makes our life a lot easier. So it's not moving up or down. So I'm pulling it with this sort of angle, but it's not accelerating upwards or downwards. And so you see this A sub y right here, that is 0. So that will make this whole right side of the equation 0. It makes it a lot easier. Okay. Now to do this, you just punch through it and then subtract it over the other side. I should also, because I see it right now, I made this mistake. No one yelled it out. It's a minus. Minus because it's down. So this force of gravity, I don't have a minus over here, but I should be putting it right there. Okay. Yeah.
What is MA sub y equals 0 then?
Because I don't have a physical thing. If I'm pulling a sled and it has this sort of force this way, it's not accelerating up or down. It's only accelerating to the right.
Sorry.
Okay, let's see. See if I could beat you guys.
I got negative 720.6. Yeah, I mean, this side.
Negative 720.
Positive 720. Let's put it to the other side.
Okay, awesome. Cool. 720. Okay, these are going to be like exactly like problems you'll see on the homework. All right, if you can understand this, this is like reaching on the hardest part of this, whole chapter. Just managing where the forces are pointing, realizing that I need to sum the horizontal pieces by themselves, and then I need to sum the vertical pieces by themselves. Okay. Let's see. 5. Here we go. You guys didn't believe me, I said I had a lot of examples today. Okay. Person finds their own weight on some flat, motionless ground as 800 newtons. This is their weight, so it's a force. Then they take the elevator into, they take the scale into an elevator, see if that value changes at all. Should it change? So it's a moving elevator, I should say. What if the elevator is moving upwards? So it seemed like they're heavy. Yeah, so they're moving up and they're being forced down into the ground, sort of. So I may be expecting that they'll weigh a little more when the elevator is going up. Maybe they'll weigh a little less when the elevator is going down. I don't know if I'll have enough room. I'm going to at least do the first one. So let's see. First, let's find out how much mass this person has. So we know their weight while at rest on the ground. So that's just a force. We also know acceleration of gravity. So (800 newtons). Okay. I think it should be about 400, 700. It's that way, 700. Yeah, okay. Yeah. So we get about 81.6 kilograms. Okay. So that will be good to know for later. What is this person's weight once they get into an elevator and it starts moving upwards? So let's see. I'll draw a rough picture. It doesn't have to be perfect. Person's weight while the elevator is moving upwards. Well, I can't make sense of that. Let's do a free body diagram. Gravity is always down, and they are moving upwards. Yeah.
Wait, where did you get 81.6 kilograms again?
So I'm just, I was given a force, and I was just curious as what their mass is.
Oh, okay.
So I went from the equation up at the top. See this one right here? That is just force equals mass times acceleration. Except you could rewrite it as weight equals mass times the acceleration of gravity. All right, so down, and we have a normal force that is now it's more than keeping it stationary. It's like if this table were to start elevating upwards. The table is forcing it upwards more than the book is forcing it downward. So it's a stronger normal force up. So I should actually draw this a bit more to scale, like this. So that's why it's going upwards. There's a larger upward force than there is a downward force. Okay. Let's sum the vertical forces. In this problem, we don't have to worry about horizontal. We're not going left and right. So we only have two vertical forces. Normal force going up and the force of gravity, or its weight, going down. And that's always equal to however it's moving. Since it's vertical, it's a sub y. Okay. So, so we know, let's go like this. Sub n plus, or no, minus, I should say. We know that when they're at rest, when it's at rest, you know, this book, a person standing on the scale, Newton's third law, I'm forcing down, the scale's forcing up. So that normal force from the scale is the same as my weights pushing down. So that means that at one point, it measured my force of gravity that's downward at 800 newtons. So I can say this value right here is 800 newtons downward. And then the mass of the person times how they are moving at that moment. In this instant, they are accelerating upward. And so that will be a positive acceleration upward. Up and to the right are always positive. Plus 2.0. I don't know why I didn't put the mass in already. Okay. So I'm going to add over force of gravity while the thing was stationary. And let me add the mass in as well. That's kind of also why we found the mass. We're going to be using it later. That's 6. Okay. What is 81.6 times 2? That's going to be 162, 163.2. Right? Yes. All right. Plus 800. So that means this person now weighs, when the elevator is moving upwards, a whole 963 newtons. So this isn't like, it doesn't mean that you like gain mass when you're moving up. It just means that you're forcing into the ground harder when the elevator is moving up. All right. And I think I can maybe skip some steps for the second part, because what's the only difference in the second part? I kept them the same sort of because I knew I might take a while on this. It's going downward. So that means it's a -2 meters per second downward. And that's the only difference in that next problem. So that means this first value right in the front right here will be negative. So let me take 800 and subtract that first value. What did I say? 163. So when the elevator is going downward, let me say like, part 1. When an elevator is going downward, you're forcing yourself into the ground less. So there is a point when the elevator might accelerate so fast downward that you don't force yourself into the ground at all, and that's like free fall. You imagine yourself in a falling elevator, you are weightless. That's what the phrase weightless means. You're not forcing yourself into anything. All right, let me say part 2 next to this. Yeah.
I just wanted to clarify something. So
Yeah.
for the force of gravity,
Yeah.
it's 800 newtons because that's the weight pushing down when it's going up?
So I'm using that initial point when I was, or I could say instead of force of gravity, I could say it's weight.
Okay.
And then
Okay.
I skipped one extra step. I could have said mass times gravity instead of that. And so that's what we've already done up there.
Okay.
Yeah. Is that kind of the same thing?
Yeah, that was actually my same question. So it's negative because it's going downwards, right?
Negative going downward, yes. All right. I can tell you guys are loving this. Okay. I think this is the last one. This is also probably the most complex one of this chapter. If you get this, you'll get like an A on this part of like a next quiz and anything. We have a block that's sliding down an incline. So imagine a piece of ice or something on a ramp. Put a block of ice, and it slides down. It's frictionless. It doesn't slow down at all. It's going to speed up. How do I find the magnitude of its acceleration? So it's not going straight down. It's going, down and kind of do an angle that way. So it's not exactly 9.8 meters per second. I want to figure out how fast it's going down at that angle. So I always start with a picture. Let's see if I could draw 30 degrees, something like that. So we have a box on an incline that is 30 degrees. All right. It's going to be moving down the ramp that way. Which direction is gravity pulling?
Down.
completely straight down, not perpendicular to the surface. That's sort of the result of what's happening. So gravity is pulling straight down, always. Doesn't matter if you're, on a ramp or whatever. So we have, I'm going to make this a little more like that. Gravity's pulling straight down. All right. Now where's the normal force pointing?
Perpendicular to the surface?
That one's perpendicular to the surface, right. That's the contact between where the thing is touching the surface. So that one is going that way. Okay? All right. Now before I get into, adding forces, we're going to be doing that anyway. You could probably already tell we need to find components of something. One of these is at an angle that we don't like. We need to cut it up into easy slices. Let's cut the bottom one, the force of gravity, up into some easier slices, x and y components. Now, the way I like to do this is take this picture and just rotate it like that. So let's rotate the picture. Let's see what happens. So in this case, the normal force is up. That's good. But since I'm doing that sort of shift, gravity is going that way, right? I should write on this. Rotates. So people know that I'm not actually like changing laws of physics by saying gravity is different. So gravity is pointing kind of that way now. Right? Does everyone kind of agree with that? Okay. So we need to find the x and y components of the force of gravity. We can do that easily by sort of doing those dotted lines how I've always been doing them. Piecing it up real easy. So like that. So I'm just going to make these one color lines. That. And even though this is like, I'm rotating and that's not quite vertical, I'm still going to call that the vertical component because that's how that's just how I'm labeling it for this problem. All right, and the horizontal. Okay, we have a problem though. We don't know where the angle is. The angle is from the ramp. Where does that relate to my new picture over there? So if we knew like some advanced geometry tricks, we're going to figure out that the angle is right here. So that is the 30 degrees. So this is like the laws of like parallel lines, where lines cross one another from geometry class. We're able to tell that angle that I just drew is 30 degrees. Awesome. So now this is a problem just like everything else we've done before. We have something that has two forces vertically and one force kind of accelerating to the right. Let me actually draw the arrows on these. Okay, and to the right. Okay, let's sum the, we only need one of the we only need to sum one of the forces, and that is the horizontal, or the, how is it moving down the ramp, that way. So let's sum the horizontal forces. That is this blue one. And that's really it. That's all of the horizontal forces. Equals the mass of the block times how it's accelerating. That's ultimately the thing we're solving for, that a sub x. Also, maybe you could see where there's like another tricky thing that's happening. Look at where the angle is. There, up there. So what kind of trig function is this horizontal component going to turn into? It's going to turn into a sine, yeah. Usually it's been cosine for all of the problems up to now. Now we need to be careful of which angle, where the angle is for what we're using. So this turns into, let me make that smaller. All right. And how do we find the force of gravity of this block, or the weight of this block? Are we given it? No. Oh yeah. We're given the mass up at the top. We're given mass, we can find the weight. So I'm going to do this up in the corner. Okay. $490. $490. Exactly? All right, awesome. Newtons. Okay, so now we have that force, we know the angle, we know the mass, we can solve for the acceleration. So let me write it all out in full, and we need to divide the mass over to the other side. That is 490 times sine of 30 degrees divided by the mass of the block, which is 50 kilograms. $4.9. 4.9. 4.9 meters per second squared. All right. I think, yeah. Negative. Sliding down, yeah. The thing is, it says magnitude, so it doesn't matter. A lot of problems just throw magnitude in there, so you don't have to worry about it. Right. So we found the acceleration of this block. If you understand this, you are like golden on large portion of everything in this class. So I think this is the last example. I do have a small thing on tension. Or no, sorry. Friction. I think I'll just do this as the last slide for today. I've done a lot of work. I gotta go to the wedding this weekend. 6 hours away. Okay, so frictional forces. A lot of the problems, that last problem I said it's a frictionless ramp. This thing's sliding down a frictionless ramp. A lot of times, things in the real world aren't frictionless. There's friction everywhere. Friction is a contact force. So whenever two things touch, there's bound to be friction somewhere. There are two types of friction. Oh, it's copying me. Static friction and kinetic friction. So, static, things that stay still, not moving. So, let's say not moving. It only leaves, the next thing we already know. Kinetic, that's the word for motion, things that move. Very energetic. This is a moving friction. Okay. I didn't write as much as I thought, so we could just finish this whole thought out. Static friction. You guys ever move your bed on the carpet, or you're trying to move furniture, anything, moving the table, sliding a book, any sort of motion where you slide something. Have you ever noticed that you give it a little push and it doesn't move, but then you get a little more, and then it kind of breaks free? So that's due to static friction. So static friction, when this book is staying still, it's sort of like the atoms and the molecules are locking together. So it's sort of holding it down. Let me draw a little picture. So imagine that box example on the table. I'm going to zoom in with a really expensive microscope to this section right here, right where they are touching. And the molecules and the atoms of what these things are made of, they're not perfectly flat. That book looks flat. This table looks flat. It's not. There are tiny little jagged peaks, bumps, valleys on everything. So the book, which is up here, has a structure, a specific molecular structure. When something stays still, it has enough time to actually settle in to the other molecular structure of whatever it's touching. So if here's the book, you see this right here, that's the table. You see, they kind of might lock together a little bit. They're not perfect. They don't match each other perfectly, but there's enough. They're sort of locked together. That's why when you give something a little push, it doesn't move. You give something a little bit more, and it kind of like breaks free when you start sliding it. This is called static friction. Every object has it. I'm going to put the equation up here. I don't think I'm going to put friction on any homework, but I'll put the equation you might need. So we have like 0 mu this. So what we have, I'm going to define this for you. So we have force of static friction this right here, this mu, that is just a number. That depends on what the material is made out of. So each specific material has a different number. That's just a value. That's that. And this is the normal force that we know. And why do I have it like 0 to the force to the force of static friction max? And that's sort of like me saying, like, I could have 0, or I could have a little bit, or I could push it all the way up to when it starts moving, and that's the maximum static friction. That's for this peak you see right here. So each object has a different sort of range or different limits. Next up, very quick. Once we've seen that, this next example is super easy. Those things that were locked together they're now sort of, you're pushing these things. You're pushing these hills past each other. They're moving so quick past each other. They're just sort of bouncing on the top of each other. And that's why this is a smaller force. So I can push it, and it takes a lot of energy or force to get it to start going. But then as soon as it starts moving, now it's a lot easier to push. And that's because of this sort of, riding on the top. They're not connected anymore. The equation of this is, let's see. So same sort of thing, except kinetic version. Force of kinetic friction and this is the normal force. All right. So we have these two things, these two versions of friction, and it's not like once you figure it out, that's it. Every object has its own coefficients right here. So depends if it's rubber or steel or ice. What are the molecules made of? What's the shape? What are the shapes of these hills and valleys? I'll leave it on this. You guys don't have to write this next one down. I just want to put it up. So this is like a chart. These are just numbers. people have gone in and actually measured these materials. So the higher the number, the harder it is to push, or greater force. So you have rubber on concrete. There's a high friction. There's a lot of friction between the two. We get to things that have low friction. Think of like railroad wheels. Think of like it's a steel wheel that's on a steel track. That's going to allow them to give more power to the wheels. It's not wasted with friction. That's why they're made of steel. You think of like, what else? Bone in the synovial fluid. Those are like your bones in your arms. It'd be awful if you took a lot of friction to move any of your joints. That's why they're relatively, actually that's the smallest one on the chart. Yeah. So these are just numbers that are sort of tested and measured. That's where I'll leave it. I'll put new homework up, due next Thursday at midnight. There's a current one due tonight. I'll see you guys later. Have a good weekend.